So continuing on with introducing the skills that you need to be successful in chemistry, we're going to look at a math review. And unfortunately, I know people do a little cringe when they hear the word math, but these are foundational skills that you should be fairly confident in. We'll look at the metric system, we'll look at some basic algebra, and we'll look at how to do some calculations that are important and based upon scientific notation. When we look at the metric system was developed in the early 1800s and has now become an almost universally accepted standard of measurement. It's based around units or powers of 10, and the advantage of that system is that to convert between one unit and another, all we need to do is move the decimal place in one direction or the other. I've got a list of metric prefixes here, up to a million millions and as low as a million millionths of a base unit. When I say base unit, that's a unit that has only a single letter to it. So a liter or a gram, a second, something that is a unit without a prefix or without a number on the front. And I've highlighted 3 here that I expect you to memorize. I'll give you a chart, and in fact I'll give you that chart as a resource for all your assessments, but I do expect that these 3 are ones that you must know. So to make units larger or smaller in accordance with what you want to measure, we use prefixes. So to convert from one unit to another, it's done simply by multiplying or dividing by powers of 10. Similarly, we can use this chart, which is one method that you can use to convert values, by simply moving the decimal point to the right or left. If this system doesn't particularly work for you and you are very confident with the method that you know, you can certainly use that. But this is another reference, another resource that you can use if other methods don't particularly work. So again, I'm going to tell you that these things are based around movements or positions relative to a base unit, and that base unit has a single letter to it. So I'm going to use an example of a liter. When we look at ones that are written on the right hand side, these all represent values that are smaller than the base unit. The first one that we see that's really important and gets used all the time in chemistry in particular is a milli, or 1,000 milliliters in a liter. 1/1000th of a milliliter, or 1/millionth of the base unit, is a micro, and it's written using the Greek letter mu, mu. Although we don't use it very often, you should be aware of the fact that 1/1000th of a micro unit, or 1/billionth of the base unit, is a nano unit, and it's written using a lowercase n. Now, when we look at values that are written on the left-hand side of this chart, these are larger than the base unit. So a kilo unit with a lowercase k represents 1,000 of the base unit, is 1,000 times larger, 3 decimal places. If you look 3 decimal places or 1,000 times bigger than a kilo unit, you have a mega unit. And if you wanted to go even farther, you could look at 1/billionth or billion of the base units, or 1,000 times larger than a mega unit, and that would be a giga. A couple other miscellaneous prefixes that you may wish to be aware of, although we don't use them very often, include deca, which represents 10 times the size of the base unit, represented with DA, is the only prefix that has 2 letters to it. Deci, which is 1/10th of the base unit, and again we've got centi there, which we've already talked about. So how is it that we use the chart? So if you're given, for example, a value of 502,495 micrometers, and you're asked to convert that into kilometers. Notice that the end, the unit that you're measuring, has to be the same. It's only the prefix that changes. What we would do is look at where we start on the chart compared to where it's asking us to end up. So we're going to start right here at the micro unit, because that's what we've got to start with. and the end position is the kilo unit. So this is what we want to end up at. So starting at the micro and moving to the kilo unit, I need to move 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal positions. So I'm going to start with my decimal position, which I know is there even though I don't write it. 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal positions. So in kilometers, 502,495 is 0.000502495 kilometers. People quite frequently will use this system and look at it and go, well, do I have to write all those digits down? We'll talk about when you write and how many digits to write on another day. So next we want to talk about some basics of algebra. What I need you to remember when we talk about algebra, because some people have a little bit of a mental block here, is that it's really just the opposite of regular math. So when we perform normal quote-unquote math, what we're doing is we're doing repeated operations where all the values are found on the same side of the equal sign. And people know that there's an order of operations that guide us in when or which order we are going to use in performing them. That order of operations is using the acronym BEDMAS. So brackets, exponent, divide, multiply, add, subtract. What we sometimes forget is that algebra just represents the opposite of regular math. So what we see is that a variable is on the same side of the equal sign, and so what we have to do is actually the opposite of our normal order of operations. So instead of using BEDMAS, this time we're going to use SAMDEB. So first we reverse the subtraction, then addition, multiplication, division, exponent, and brackets. So let's look at a couple of examples here. If we have 2x plus 4 equals 20, and I know that some people are very confident in looking at this and going, oh, well that's quite simple, but let's look at how this actually happens. We'll notice that we have the variable x on the same side of the equality as other numbers. This is algebra. So to reverse it, I need to do the opposite of the operations in the order of SAMDEB. So the first thing I'm going to do is move or remove the addition by doing the opposite of that operation, or subtracting. So I'm going to subtract both sides, 4, so we'll have that 2x equals 16. Again, we've got a value on the same side of the equation as a variable. So to reverse that, all I have to do is the opposite operation to a multiplication. So in this time, I'm going to do a division by 2, and we see that x now equals 8. The last piece of math that we need to talk about is scientific notation. And because chemists deal with exceptionally large numbers, and exceptionally small numbers, we have to have a way of working with these digits and these numbers without actually having to write many zeros, which can lead to really easily to transposition or copying errors. So the method that we use is called scientific notation. To write a number in scientific notation, very simply, all we have to do is write a number expressed as a value between 1 and 10 raised to a certain power. So if we're taking a value and converting between decimal and scientific notation, what we need to do is count the number of times you move the decimal point to produce a value between 1 and 10. That number of times becomes the exponent on the power of 10. And what we see is that if the value is positive, that means that the initial value is greater than 1. If the exponent is negative, the initial value was smaller by a certain number of decimal places, and as a result was moved to the right. So let's look at an example. If we're looking at 519,000,000, and you want to write that in scientific notation, I'm just going to change my pen color here so that we can see what I'm doing. I first want to write a number between 1 and 10. So in this case, I'm going to move my decimal so that it's between the 5 and the 1. Next thing I have to do is count how many times did I move the decimal to get it to that position. So initially it was here and I moved 1, 2, 3, 4, 5, 6, 7. To write my final value, this becomes 5.19 times 10 to the 7. On the flip side to that, if we had a value that was very, very small to start with, and I wanted to write that in scientific notation, again I need to write it so that I've got a value between 1 and 10. So I'm going to move the decimal place from here to between the 2 and the 0, producing a value of 2.01, again between 1 and 10. How many times did I have to move that? Well, I moved it 1, 2, 3, 4, 5, 6 times this time. So this is 2.01 times 10 to the 6. But you'll notice that the value was initially very small, and I moved the decimal place in the opposite direction. So because I changed it from a very, very small number into a larger number, the exponent is negative. Doing calculations in the opposite way from scientific notation to decimal notation is exactly the opposite. So I'm going to take my mantissa, that number at the front, I'm going to move the decimal point the number of places that are indicated by the exponent. Remember that the decimal place gets moved to the right if the exponent's positive, because a positive exponent means that the value was initially very, very big. The decimal place gets moved to the left if the exponent is negative, and that's because the value was initially very, very small. So let's look at an example of how to do this. If I have 9.25 times 10 to the negative 12, this is going to be a lot of zeros, which will show you exactly why it is that we want to do or use scientific notation. We'll change our color. I'm going to take my initial value, 925, and I'm going to move the decimal place 12 times. Because we have a negative exponent, that means that the value should be small, meaning that I need to move the decimal place to the left. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 positions, and obviously I'm going to fill those extra place values in with zeros. So as you can see, this is exactly why we want to use scientific notation. And if you can believe, the values that we'll be dealing with later in the year are much, much, much bigger and much, much, much smaller than this, so would have many, many zeros. So next day we're going to be looking at how to practice calculations with these skills, but I just wanted to introduce to you exactly what they were before we started.